Hey guys, we're going to finish off today the portion on astronomy. In the last video, I ended with apparent brightness and absolute magnitude, and the differences between the both, and how the atmosphere plays a part in distorting our vision or a sense of reality of what's real. Because on Earth, we might think that this star is closer and brighter compared to another one, and in reality, it isn't. So getting into outer space and measuring from a standard, point in space, measured out without the interference of the atmosphere is absolute necessary. And don't downplay the importance of this, because this actually is one of the factors of the many that go into the how big the universe is, the speed of light, and basically when the universe was created. So absolute magnitude and apparent brightness is very important in getting that information. All right, so the next topic, and actually let me show you a picture of some of this real quick. I think I have them already pulled up. Like a starry night, I have different pictures of stars, and we might think that certain ones are brighter or closer than others. Like this right here would be a great example where I'm putting the pointer. And then we think that one might be brighter or closer, but this one right here, right next to it, actually might be closer to us. And getting in outer space would be a great way to avoid the interference that our atmosphere actually gives us and get an accurate measurement of the universe and how big it is. It's important for definitely for astrophysics, and goes all the way down into our belief system in regards to the creation of the universe and how old it is. All right, so a very important topic. We're going to go now down to classifying stars based on temperature. Temperature, the blue stars are burning the brightest. They are hot, hot, hot in comparison to what we see here, like Betelgeuse. The older you are, you burn a different color. You kind of lose your energy and you burn like a reddish orange. That means that basically you're kind of on your way out the door. The ones that are burning really bright and they're younger, that's going to be the ones that are burning blue. Now, the bigger you are in regards to the star size, your life is not as long. You use up all your energy and you die quick. Where the ones that are medium sized, like our sun, a medium sized star that will become a red giant, is going to have a much longer lifespan than something like Betelgeuse. Betelgeuse used to burn bright and he used to burn blue, but he used up all his energy relatively quick in regards to, astronomical terms. He used up his energy pretty quick and he's on his way out. All right, so again, the bigger you are, shorter lifespan. If you're young and you're going to be burning bright, you're going to be burning with a bluish white color. Okay, stars, classifying stars based on size. Yeah, this will go into whether you're going to be a red giant or super red giant. And again, super red giants use up all their energy pretty quick in regards to astronomical time, and they're out the door. Out the door. The ones that are smaller, they're here longer. And Betelgeuse he's a super red giant, but he's small in comparison to some. Antares, you can see, is bigger than Betelgeuse, and the largest super red giant, it slips my memory right now, but makes these guys look very, very small by comparison. And our sun, in comparison to Betelgeuse and Antares, is a 1 pixel. You can't even hardly see it on this image. If I expanded the image out, you might be able to see a little bit, but see it says sun 1 pixel, and right. In comparison to these guys, and about 1 million Earths can fit into our sun. So it kind of shows you how small we are in comparison to some of the bodies out there in space. Okay, going down here to the next topic. The next topic is basically measuring the size of our universe, and this ties into the absolute magnitude and apparent brightness that I was speaking about earlier. Because the size of our universe is really determined a lot by the speed of light. And the speed of light is 186,000 miles per second, so it's really quick. And the speed of light does not measure time. If we say 1 light year, we're not measuring time, we're measuring the distance that light will travel in a year, going that fast, going 186,000 miles per second. So the distance it will travel in 1 year going that fast, that's what we mean when we say 1 light year. Now, the universe is almost 14 billion light years across. And again, we get some of that information from measuring the distance of stars from a standard distance or standard point in space. See how everything ties around now? Our closest star besides our sun is Alpha Centauri, and you can see that's 4.3 light years away. So going that fast right there, 186,000 miles in 1 second. If you could go that fast, it would take you 4.3 years to get to the next star besides our sun. All right. Now this is talking about the Hertzsprung-Russell diagram. And what I briefly talked about earlier in my previous video, it really just shows two main things, luminosity and temperature. So the luminosity is over here, and luminosity is the brightness, and temperature is down here. So as we go on the Hertzsprung-Russell diagram, this is a protostar. These are where stars are born at. And basically they're very small at this point. They're basically a nebula. And gravity's pulling the nebula in and it's forming a star, and we would call that a protostar. These guys are going to be burning red and very, very dim. See, luminosity, very dim. So very cold and very dim. As they work their way up, and see, there's our sun right there. It says sun. Maybe I can make this, I can't make that bigger, I'm sorry. Our sun is right there. As they go up the Hertzsprung-Russell diagram, look, the temperature increases. And also, as they grow on the Hertzsprung-Russell diagram, their luminosity increases, their brightness increases. So as they go up, red giants are going to start making their way over here. And if you go into a super red giant, you're going to go all the way up, and you see Rigel there, and Betelgeuse is over here where it used to be over here. It goes up, and then it makes its way over. And then it has a death sequence. And determining on what you are, whether you're a red giant or a super red giant, determines on your death sequence. And I might talk about that here in just 2 slides. I think I'll talk about the death sequence of these guys. All right, so yeah, let's go down here to the birth of a star. And that's what I was saying just a second ago. Stars are born from pre-existing stars, or the death of pre-existing stars, or maybe a collection of nebula gas from the original Big Bang. Either way, here we see I think it's called the Horse Nebula. I'm not sure. Yeah, I'm pretty sure this is the Horse Nebula because it's the horse hit right there. This would be, oh my gosh, this would be really big. This is light years and light years and light years across. I don't want to say an estimate because I'd just be guessing. I don't know. But I do know it's light years across. Now, inside this, and we're looking back in time when we look at this picture because it took time for this image to even get to our telescopes. But definitely there'll be some coalescing of the gases to form new stars. And this nebula would have been made more than likely from a pre-existing supernova explosion, if I had to guess. So maybe you can write that down. How the Horse Nebula formed? Was it from a previous supernova explosion? If that's something you want to do, again, off the top of my head, I'm willing to admit I don't know. But if I had to guess, I would say yes, that comes from a pre-existing supernova explosion. This is many light years across, and this will form new stars in the future. If not, it's maybe already doing it because we are looking back in time at this. Okay, and nebulas are mainly, the main composition of these gases would be hydrogen and helium. Now, there are definitely some other gases in here, especially if it's made from a supernova explosion, because that's what gives us our new elements that we have. The elements inside you were created by a supernova explosion. So whenever we have a supernova explosion, we do have new elements being made. But the main gas still overall would be hydrogen and helium in this nebula. Go with hydrogen if you have both of them as an option. Okay, and I'm about to run out of time, and I still have these 3 slides to go. So unfortunately, I have to do one more slide talking about how this sequence happens, or the sequence of death happens for these red giants and super red giants. So I'll see you in one last video. Thank you for watching.